Okay, looking back at the redox reaction, I should mention one thing, and that is if we have a potassium permanganate, so we have permanganate, and we have hydrochloric acid, so we have chloride, acid, and water. And so when we look at that mixture, the inventory, and we compare chloride versus water, which one should be easier to oxidize, chloride or water? Water should be easier to oxidize. But in this particular reaction, chloride is oxidized, water is not. So this is the one, and this is the only exception on this chart. And the reason that chloride is oxidized instead of water is because of difficulty in oxidizing water. When we oxidize water, you have to break bonds. When you oxidize chloride, you just strip an electron from the outermost shell. And so the ease of oxidizing chloride is easier, but you don't get as much return, that is energy return. Here you get a bigger energy return, but the investment is greater. And so this is like if you invest a little bit of money, you'll get a little return, quick and easy. But if you invest more money and you spend a lot more time doing work, you could get a bigger return. And so in nature, it just takes the easy way. It just takes a quick return with chloride. And so that was one thing I'll mention. You don't have to have that memorized. In Chem 1A or Chem 1B, you do, but so that particular equation has a little distinction to it. But once we make the chlorine, then this is showing we got to take the diatomic chlorine. The diatomic chlorine is going to look like this as far as a Lewis type structure goes. We break that into chlorine atoms and then it reacts. When this reacts, we form the sodium ions. The sodium ions turn out to be about half the size of the original parent. We lose an electron, and now we have 11 protons with 10 electrons. 11 protons with 10 electrons will pull the electrons in closer. And so when we form cations, the cations are typically about half the size of the parent. When we form anions, now chlorine has an extra electron it has to watch. Well, it's harder to watch because it doesn't have enough protons. And so when we form an anion, it doubles in size. And so when we form a cation, it shrinks by about half. And so cations tend to be smaller than anions. And so when we do the lattice structure is we're just putting the positive sodiums and the negative chlorides. And so we just try to put as many of these as possible. So you'll notice that the chlorides are bigger than the sodium. That's opposite of what we just saw. And the reason is because of the what happens to the size when we have too many electrons or too many protons. And so the sodium chloride lattice, let's take a look at that. NaCl lattice. This is your typical salt type lattice, which is here. And so we can tell which ones are the sodium and which ones are the chloride. Now, when we're looking at the elements, the sodium is bigger than the chlorine, but when we look at the ions, it flips. And so the sodium ions are the purple, the chlorine ions are the green. And they just pack together, they try to maximize. Each positive ball wants to be in contact with as many negatives as possible, and each negative ball wants to be in contact with as many positives. This is called what's that called again? A lattice. So we end up, ionic compounds form lattice structures. And so the Lewis structure just shows one formula unit of the lattice. And there are many, many formula units in the lattice. But this is the Lewis structure of sodium chloride here. All right, so let's move on. Sodium is what we call an alkali metal. Alkali metals, alkaline earth metals tend to lose electrons. Chlorine is a halogen. We have the alkali metals, alkaline earths. These lose electrons easily. These have lower ionization energies. Over here, these don't want to lose electrons. These would rather gain electrons. Very low ionization energies. Alkaline earths lose 2. Halogens gain. So here we have the alkali metals and the alkaline earth metals. Noble gases, hydrogen. There's chlorine, that green gas over here. All these are oxidizers. Turns out the smaller it is, the more powerful oxidizer. So fluorine is the smallest, the most powerful oxidizer. Iodine is the biggest. Astatine is the radioactive. We group things in terms of metals. Metals lose electrons, non-metals gain electrons. These tend to lose, these tend to gain. These can go either way, lose or gain. In the middle. Well, all these can lose and all these can gain. Depends on metallic character. We'll look at that later. Let's go back to this. Chapter 12. So start going back through the redox reactions. Make sure you understand those before the test. We can cover those before the test. If there's any questions regarding those. So this is the formation of sodium chloride from sodium metal and chlorine gas. Very violent reaction. Here's what's happening with the sizes here. When sodium loses an electron, it shrinks to about half the size because we got 11 protons and 10 electrons. When chlorine gains an electron, it doubles its size. Because now we got 17 protons, 17 electrons, going to 17 protons, 18 electrons. 18 electrons are harder to handle than 17 protons. Here's the lattice. Another view of the lattice. This is an expanded view of the lattice, so you can see the connections. The sodium ions are gray, the chloride ions are green. Lattices don't conduct electricity very well. You know, these are non-conductors because it's missing mobility. You know, there's no translational mobility in solids, so the ions are stuck. However, if you melt this, then it conducts electricity very well. Because if you melt it, then you've got translational mobility. And so this is a molten salt. You know, molten salts conduct electricity. It's a liquid salt there. It's kind of viscous. You can see it's pretty viscous there. It is conducting electricity. Aqueous salts also conduct electricity. Aqueous salts, you've torn apart the lattice. So salt water conducts electricity very well. Look at this ionic bonds. Now, what happens in covalent bonds is this. You know, here chlorine's a very powerful oxidizer, and sodium's ionization energy isn't so great. You know? And so it's easy for chlorine to strip the electron off sodium. However, what if chlorine had a more formidable opponent? You know, let's say, what if chlorine wants electrons? Right? This needs one more electron to fill its octet. And so let's say chlorine encountered another chlorine. If chlorine encountered another chlorine, then that chloриne's still going to try to take the electron because it wants to take electrons. So it's going to try to take this electron. However, this chlorine will also try to take an electron. It will try to take that electron. Is there going to be a winner and a loser? No. You know what's going to happen? In the other example, sodium's the loser. Sodium's the loser because its ionization energy isn't so big, but chlorine's ionization energy is big. And not only that, this should be a tie. Well, if it's a tie, you know, are they just going to give up and go their own way? No. What's going to happen in a tie is this. The two chlorines are going to end up sharing. Obviously, each chlorine wants its own, but in this case, this is the next best compromise. When the two chlorines end up sharing like this, then what we can do is we can gain. What we can do is we can gain the octet of electrons, 2, 4, 6, 8, for this chlorine, and an octet of electrons for this, but we just have to double count those. And so if those belong to both, then we can get that octet. And so this is the chlorine molecule. And this is what we call a covalent bond. A covalent bond is the sharing of electrons. Covalent bond. An ionic bond is when winner takes all. Covalent bond, we have sharing. Now, with the covalent bond here, we could represent it another way. The other way is each pair of electrons is represented by a line. And so this is showing the covalent bond here. These are two ways of showing the covalent bond. Well, the more common way is to show it by a line, like this. We have sharing. And so ionic, winner takes all, covalent, sharing. But, well, we can have something like this. So this is covalent, that was ionic. What if we have something like hydrogen? What's harder to ionize? Let's take a look at the periodic table. What's harder to ionize? Sodium or chlorine? It's harder to strip an electron off, but chlorine. Chlorine's smaller. Plus chlorine doesn't want to lose electrons, but it can lose electrons, like in perchlorate. Perchlorate it loses several electrons. What's harder to ionize? Sodium or hydrogen? Which one's bigger, sodium or hydrogen? Sodium's bigger, therefore it's easier to ionize. Hydrogen's smaller, therefore it's harder to ionize. And so now we have, we're going to set up a match between hydrogen and chlorine. Hydrogen and chlorine are going to struggle for the electron. Over here was an even match. This is a tie. Over here, hydrogen is a lot stronger than sodium. Therefore, it doesn't really want to lose. And so what happens here is we end up forming a covalent bond. This. And it would look like this. But this bond we call a polar covalent bond. And so let's show the three types of bonds that we've discussed so far. And that would be the ionic bond. In an ionic bond, sodium lost, chlorine gained all of the electron density. So this is ionic. Ionic is winner take all. Winner take all. And therefore, that electron density belongs entirely to chlorine. I'm going to draw using the cloud like this. But hydrogen proved to be a more formidable opponent, and it didn't lose it. And so for hydrogen, we represent it like this, a sharing of electrons. But it's an uneven sharing. When we have an unequal sharing, well, it turns out chlorine is stronger than hydrogen, but hydrogen is not so weak to lose it all. And so the cloud's like this. Hydrogen holds on, but chlorine gets most of it. This is the polar covalent bond. Where hydrogen holds on to it. So the polar covalent. And then we have the purely covalent bond, which is two chlorines. The two chlorines, they're going to have to share equally. In hydrogen and chlorine, they don't have to share equally. It's unequal sharing. Chlorine gets most of it. In Cl2, it's totally equal. So we end up with a situation like this. This would be purely covalent. The dots around here, Yeah, those are dots representing the electron cloud. The electron cloud. We have two electrons there, so the electrons, because of the Heisenberg uncertainty principle, are represented by some kind of cloud. The probability of finding electrons right on chlorine is high here. Here, you know, kind of uneven, mostly around chlorine, sometimes around hydrogen. Here, around both equally. That's what it represents, those. So hydrogen either wants an electron or one electron or loses one electron. So if I have a hydrogen here, here's a 1s orbital, here's an electron in the 1s orbital. So we could either fill the first shell with 2 electrons, or we could lose it. In this case, we're going to try to fill it. So hydrogen is going to try to take an electron to form hydride, but if it tries to take an electron from another hydrogen atom, it's going to result in a tie. And so this is the tie here. So if we look between the 2 nuclei, this is the cloud. It's very symmetric cloud. That's a covalent bond that results there. So that's the hydrogen molecule, H2. It's fluorine. Fluorine would form a covalent bond. It would be a very symmetric cloud there. There's 2 representations of fluorine here. Lone pair in the octet rule. When we look at this, we call these things different. For example, these are lone pairs because these pair of electrons belong just to this chlorine. This is called a bonding pair. The bonding pair is shared. The bonding pair is not specified there. And then we have the octet rule. The octet rule is we need 8 electrons surrounding the atom, and we could double count this way. So here I have 3 lone pairs and a bonding pair. That makes it 8 electrons. Around here I have 3 lone pairs and a bonding pair. It's 8 electrons. That's the octet rule, 8 electrons. And so chlorine can get 8 electrons by either sharing or taking. If it shares, it's called a covalent bond. If it shares evenly, it's a covalent. If it shares unevenly, it's a